Hi everyone. Today we're going to be completing our notes on 7-7 factoring special cases. These are some quick notes. We're going to discuss one type of special case of quadratics that we're going to factor. A binomial in the form a squared minus b squared is called a difference of two squares. It's the result of multiplying a minus b times the quantity a plus b. So we can find the factorization of a squared minus b squared equal to the quantity a minus b times the quantity a plus b. We call this a difference of squares because a squared is a perfect square and b squared is a perfect square, and we're taking the difference of these two. So we call it a difference of two squares. So we can use this factorization, this general form for factorization, whenever we have a difference of two perfect squares. So let's take a look at example 1, x squared minus 9. So I have to first recognize, is this a difference of squares? Yes, it is. The reason why is because x squared is a perfect square of x, and 9 is a perfect square of 3. So 3 squared is 9. Okay? So therefore, this is equal to x squared minus 3 squared. And so then we can use this as the factorization, x plus 3 and x minus 3. Okay? Yes, you can flip these around and say x minus 3 times the quantity x plus 3. Multiplication is commutative, so it's okay to switch around those factors. It's the same result. Okay? Factor each expression. So letter A, we have x squared minus 64. This is equal to x squared minus 64 is a perfect square of 8. So then we know that this is x squared minus 8 squared, or the factorization x plus 8 times the quantity x minus 8. Letter B, I notice that we have a perfect square. This is, again, a difference of squares. 9x squared. If I were to see what is this a perfect square of, well, I know that x squared is a perfect square of x, and 9 is a perfect square of 3. So I can write this as the quantity 3x squared. 49 is a perfect square of 7, and so what we have, again, is the difference of squares. This is equal to 3x plus 7 times the quantity 3x minus 7. Okay. Letter C. Here we have 4x squared minus 25y squared. Well, 4x squared is equal to the perfect square of 2x, and 25y squared is the perfect square of 5y. So then what we have is the factorization 2x plus 5y times the quantity 2x minus 5y. All right. So you might have noticed a pattern that each of these factors are looking exactly the same except for the operator in the middle, the operation. It's plus and then minus. Okay. But otherwise, those quantities are exactly the same. Let's try example 2. What is the side length of a square with an area of 25 minus x squared? Well, because this is a square, that tells me that the area is equal to the side length squared. All the sides of a square are congruent, or they have the same measure. So all of them are equal to, we'll say, s. Okay? So if the area is s squared, well, that tells me that the area is 25 minus x squared. That tells me that each of those factors must be exactly the same. So if we factor 25 minus x squared, I know that 25 is a perfect square of 5, and x squared is a perfect square of x. We get the factorization 5 plus x times the quantity 5 minus x. Well, if I know that they must be equal, so area is equal to the product, well, that tells me that each of those side lengths must be equal to one another. Okay, so we can set each of those factors equal to one another. So solving this equation for x, we add x to both sides. What we get is 5 plus 2x is equal to 5. Subtracting 5 from both sides, we get 2x is equal to 0. And then finally, dividing both sides by 2, we get x is equal to 0. So if we know that s is equal to 5 plus x, which we know x is equal to 0, or you could say 5 minus 0, it's the same thing, then we find that s is equal to 5. So the side length is equal to 5. All right. Last one for today. Is the expression x squared minus 50 factorable? Explain why or why not. Take a moment and think about it. This expression is not factorable, okay? Or at least where the factorization has integers or whole number values. So this would not be factorable in that sense. The reason why not, it has to do with that 50. 50 is not a perfect square, okay? It's not a perfect square. If it was a perfect square, then we could use the difference of squares factorization to factor this. So think about just those examples of perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, and 15 squared is 225. I'd say if you're comfortable all the way up to 10 squared, you're in pretty good shape. Knowing a little bit higher than that, like 11 and 12, is really great. All the way up to 15 is even better. But I would say the more comfortable you are with these perfect squares, 1, 4, 9, 16, 25, and so on, the more easy it's going to be for you to recognize these differences of squares, okay? So I would say get comfortable with these perfect squares. It's going to help in the long run. These pop up a lot in math, and it helps us simplify, reduce factor expressions, things like that. Okay. So this has been our notes on factoring special cases, particularly differences of squares. We're going to get a lot of practice, so we'll see you tomorrow. Have a great day, everybody. Goodbye.